Welcome everyone to today's lecture on quantities and chemical reactions, Chapter 8 in our course. This chapter is a cornerstone in understanding how much of each substance is involved or produced in a chemical reaction. Whether it's in the lab or in real-life applications like medications or energy production, stoichiometry gives us the quantitative tools we need. Let's dive in. Let's begin by connecting chemistry to a real-world issue, global warming. When we burn fossil fuels like octane, which is a component of gasoline, we produce water and carbon dioxide. While water vapor is relatively benign, carbon dioxide is a potent greenhouse gas. Over time, increasing levels of CO2 have been linked to global climate change. Today, we'll not only look at the chemistry behind combustion, but also the impact of stoichiometric relationships on these large-scale environmental effects. Now, how does CO2 contribute to global warming? Think of greenhouse gases like a glass roof of a greenhouse. Sunlight comes in, but heat gets trapped. This slide shows that greenhouse gases, particularly CO2, allow visible light to enter the atmosphere, but prevent heat from escaping back into space. As a result, the Earth retains more thermal energy, which leads to a gradual increase in global temperatures. Let's look at a specific chemical reaction, the combustion of octane. The balanced equation here is 2 molecules of octane plus 25 O2 produce 16 CO2 plus 18 H2O. This tells us that for every 2 moles of octane burned, we get 16 moles of carbon dioxide. This simple ratio allows scientists to calculate exactly how much CO2 is released when gasoline is burned, something we'll be practicing in this chapter. We can use stoichiometry to go big, really big. Since we know how much fossil fuel the world burns each year, we can use balanced equations to estimate how much CO2 is released globally. Interestingly, those calculations align closely with what we actually measure in the atmosphere. This provides strong evidence that human activity, specifically fossil fuel combustion, is driving the increase in atmospheric CO2. Now we move into the heart of today's lesson, stoichiometry. Stoichiometry is the numerical relationship between the quantities of reactants and products in a balanced chemical equation. It's like a chemical recipe. If we know how much of one substance we have, we can calculate how much of another substance is needed or produced. This skill allows us to answer practical questions like how much product will form, how much reactant is needed, or whether we'll have anything left over. To help you understand stoichiometry, let's use a familiar analogy, making pancakes. Imagine you have a recipe. It might say you need 2 eggs to make 5 pancakes. This recipe represents a fixed ratio, just like a chemical equation. If we have a certain number of eggs, we can figure out how many pancakes we can make. The same concept applies when we're working with molecules and moles in chemistry. So here's the key idea. If the recipe says 2 eggs make 5 pancakes, then we can write that as a ratio. 2 eggs correspond to 5 pancakes. This is exactly like saying 2 moles of substance A produce 5 moles of substance B. Once you understand the ratio, you can scale it up or down depending on how much of each ingredient or chemical you start with. Let's apply that idea. If we now have 8 eggs, and we assume we have enough of everything else, how many pancakes can we make? Using the ratio from earlier, 2 eggs produce 5 pancakes. 8 eggs produce X pancakes. So we set up the proportion 8 eggs times 5 pancakes over 2 eggs equals to 20 pancakes. That's how stoichiometry works. We use ratios from a recipe or a chemical equation to predict outcomes. Let's now shift from cooking to chemistry. A balanced chemical equation is like a chemical recipe. It tells us how many moles of each substance react and how many moles of product are made. Take a look at this example. 3H2 plus N2 produce 2NH3. This equation tells us that 3 moles of hydrogen gas react with 1 mole of nitrogen gas to produce 2 moles of ammonia. Just like in cooking, if we know how much of one substance we have, we can calculate how much of the others are involved. This is called a mole-to-mole conversion, and we'll be practicing it throughout this chapter. Let's take a closer look at the ammonia synthesis reaction. 3H2 plus N2 produce 2NH3. This balanced chemical equation tells us that 3 hydrogen molecules react with 1 nitrogen molecule to form 2 molecules of ammonia. We can express these ratios as 3 H2 molecules to 1 N2 molecule to 2 NH3 molecules. These ratios are essential because they help us predict how much product will form or how much reactant is needed. But in the lab, we don't usually count molecules, we count moles. So we take those same relationships and express them in moles. 3 moles H, 2 to 1 mole, and 2 to 2 moles NH3. These mole ratios are what we use in stoichiometric calculations. For example, if we know we have 3 moles of hydrogen and excess nitrogen, we can use the ratio to calculate how many moles of ammonia will be formed. Now let's flip it around. Suppose we have 3 moles of nitrogen instead and more than enough hydrogen. The mole ratio tells us 1 mole N2 produces 2 moles NH3. So 3 moles, N2 can produce 6 moles, NH3. That's how we use mole-to-mole conversions in a chemical context, just like scaling up a recipe. Let's apply these ideas to a real-world situation, fuel combustion. Here's the balanced equation for octane combustion again. 2C8H18 plus 25O2 produce 16CO2 plus 18H2O. If we don't have enough oxygen, the combustion becomes incomplete, producing pollutants like carbon monoxide, CO, and ozone, O3, both of which are harmful. This is why the Clean Air Act of 1990 required oil companies to add oxygen-containing compounds to gasoline to ensure more complete combustion. Initially, oil companies used a compound called MTB, methyl tertiary butyl ether, to increase the oxygen content in gasoline. While effective, MTBE doesn't break down easily in nature and started contaminating drinking water through spills and leaks. As a result, ethanol, made from fermenting grains, replaced MTBE as a cleaner and biodegradable alternative. Although ethanol was more expensive at first, it became a safer and more sustainable solution. Up until now, we've been using mole-to-mole conversions, but in real life, we measure substances by mass, grams, not moles. So we need to learn how to convert mass of one substance into mass of another. This is where the full power of stoichiometry comes in. We go from grams to mole ratio to moles and then to grams. The balanced equation still provides the mole-to-mole ratio, and we use molar mass to switch between grams and moles. Let's do an example. Suppose an automobile burns 500 grams of pure octane, C8H18. We want to know what mass of carbon dioxide, CO2, is produced. We start with the balanced equation. 2C8H18 plus 25O2 produce 16CO2 plus 18H2O. Step 1 is to convert 500 G of octane into moles using its molar mass. Then, using the mole ratio between octane and CO2, we find moles of CO2. Finally, we convert that to grams. Here's the solution map for that problem. We start with the mass of octane, convert to moles using the molar mass, apply the mole-to-mole ratio from the balanced equation, and finally convert the moles of CO2 into grams using the molar mass of CO2. This multi-step process is typical in stoichiometry problems, especially in nursing and clinical chemistry applications where dosages and yields must be carefully calculated. Let's revisit our pancake analogy to understand limiting reactants and yield. The recipe calls for 1 cup flour plus 2 eggs plus 1 TSP baking powder produce 5 pancakes. If you have more than enough of 2 ingredients, the third limits how much you can make. Just like in a chemical reaction, one reactant limits how much product can form. That's your limiting reactant, and it determines the theoretical yield. Now suppose you have 3 cups flour, which can yield 15 pancakes, 10 eggs, which can produce 25 pancakes, 4 TSP baking powder, which can produce 40 pancakes. Even though you have plenty of eggs and baking powder, you're limited by the flour. That makes flour the limiting reactant and 15 pancakes your theoretical yield. This concept is critical in lab settings where you often need to identify which chemical will run out first and thus stop the reaction. Now let's take it one step further. Imagine that you start making your 15 pancakes, but 3 burn and 1 falls on the floor. So you only end up with 11 pancakes. In chemistry, we call this the actual yield, the amount of product you actually get in the lab. It's often less than what you theoretically could have made due to side reactions, spills, or inefficiencies. This happens all the time in real chemical reactions. Just like with the pancakes, the perfect yield is rare. This brings us to percent yield. It's a way to measure how efficient your reaction is. The formula is percent yield equals to actual yield divided by theoretical yield times 100%. In our pancake example, we got 11 pancakes instead of the 15 we expected. 11 divided by 15 times 100% equals 73% yield. In the lab, this percentage helps chemists evaluate the success of a reaction and figure out if improvements are needed. In the real world, actual yield is determined experimentally. It depends on many factors like reaction conditions, temperature, pressure, and purification steps. Usually the actual yield is less than 100%. Sometimes it's much lower, especially in complex syntheses. Knowing the percent yield helps researchers optimize the process to save time and resources. Let's summarize these key terms because they come up often in both exams and lab work. Limiting reactant, the substance that runs out first and stops the reaction. Theoretical yield, the maximum amount of product that can be formed assuming perfect conditions. Actual yield, the amount of product actually collected from the reaction. Percent yield, the efficiency of the reaction, actual yield divided by theoretical yield expressed as a percentage. These concepts are central to mastering chemical reactions. Let's apply what we've learned to an actual chemical equation. Ti plus 2Cl2 produce TiCl4. Suppose we're given 1.8 moles of titanium and 3.2 moles of chlorine gas. We need to figure out which one is the limiting reactant and what the theoretical yield of titanium tetrachloride, TiCl4, is. First, we use the mole ratio to see which reactant is used up first. That's the limiting reactant, and it controls how much product can form. To solve this problem, we use what we call a solution map. It helps us visualize the step-by-step path from the given information to the answer. We start with both reactants, 1.8 moles of T1 and 3.2 moles of Cl2. Then we calculate how much product can be formed from each using the mole ratios from the balanced equation. Whichever reactant produces less TiCl4 is the limiting reactant. That's the one that runs out first and limits the reaction. Now we apply the mole ratios. From the equation Ti plus 2 Cl2 produce TiCl4, we see 1 mole Ti produces 1 mole TiCl4. 2 moles Cl2 produce 1 mole TiCl4. So 1.8 moles Ti produce 1.8 moles TiCl4. 3.2 moles Cl2 times 1 mole TiCl4 over 2 moles Cl2 equals 1.6 moles TiCl4. Chlorine gas produces less titanium tetrachloride, so chlorine is the limiting reactant. And the theoretical yield is 1.6 moles titanium tetrachloride. In industrial chemistry, choosing the limiting reactant is a strategic decision. Often, chemists choose the more expensive or harder to remove reactant to be limiting. Why? Because if it's completely used up, there's less of it left to purify or recycle. In the lab, we usually work with grams. So our next step is learning how to calculate limiting reactants when masses, not moles, are given. Let's try a mass-based example using sodium and chlorine. 2 Na plus 1 Cl2 produce 2 NaCl. Suppose we're given 53.2 grams of sodium, 65.8 grams of chlorine gas. We need to determine the limiting reactant, the theoretical yield of sodium chloride, NaCl. We'll convert each mass to moles, then use the mole ratio to see which reactant produces less product. Here's our plan. Step 1, convert grams of Na and Cl2 to moles using their molar masses. Step 2, use the balanced equation to find how many moles of a nacelle each can produce. Step 3, identify the limiting reactant. It will produce the smaller amount of NaCl. Step 4, use that number of moles to calculate the theoretical yield in grams. This method works for any mass-to-mass stoichiometry problem, and we'll be practicing more of these in lab. Let's continue with our sodium and chlorine example. Suppose we carried out the reaction and collected 86.4 grams of sodium chloride as our actual product. To calculate the percent yield, we need to compare this actual yield to the theoretical yield we just calculated using stoichiometry. The formula again is percent yield equals to actual yield divided by theoretical yield times 100%. This gives us a sense of how successful or efficient the reaction was. Let's try another example involving the reaction. Cu2O plus C produce 2Cu plus CO. Suppose we have 11.5 grams of copper 1 oxide, 114.5 grams of carbon. We want to find the limiting reactant. The theoretical yield of copper. We'll follow the same steps, convert to moles, use mole ratios, and determine which reactant limits the amount of copper produced. To solve this, we use the following relationships. Molar masses. Cu2O is 143.10 G per mole. C is 12.01 G per mole. Cu is 63.55 G per mole. Mole ratios. 1 mole copper, 1 oxide produces 2 moles copper. 1 mole carbon also produces 2 moles copper. We apply these ratios and masses to calculate how much copper can be made from each reaction. Using our solution map, we calculate. Moles of carbon is 11.5 grams divided by 12. 0.1 grams per mole. Moles of copper 1 oxide equals to 114.5 grams divided by 143.10 gram mole. Then we apply the stoichiometry. Each gives us a certain amount of copper in moles. The limiting reactant is the one that produces less copper. That's the one that runs out first and limits the amount of copper we can get. Let's say after the reaction, we isolate 87.4 grams of copper. To calculate the percent yield, we again compare this actual result to the theoretical yield from our stoichiometry. Percent yield equals to 87.4 grams over theoretical yield times 100%. This helps us evaluate lab success. If the percent yield is low, we may have lost product due to spills, incomplete reaction, or loss during purification. That's why precise lab technique matters. Let's shift our focus from quantities to energy. Every chemical reaction either releases or absorbs heat. If heat is released, the reaction is called exothermic. If heat is absorbed, it's called endothermic. We use a property called enthalpy, denoted as delta H, to measure the heat flow during a reaction, assuming it happens at constant pressure, which is common in everyday conditions. We define the enthalpy of reaction, written as delta HRXN, as the amount of thermal energy that flows when a reaction occurs. This value helps us understand how much energy is involved, which is especially important in healthcare settings. For example, in metabolic reactions or drug interactions that either release or require energy. The sign of delta H tells us the direction of heat flow. A negative delta H means energy is leaving the system. This is exothermic. A positive delta H means energy is being absorbed. This is endothermic. Think of it like a bank account. Negative delta H means withdrawal. Positive delta H means deposit. Understanding this sign helps us predict temperature changes during reactions. Let's look at the two types visually. In an exothermic reaction, energy is released into the surroundings, often seen as heat or light. Combustion is a classic example. In an endothermic reaction, energy is absorbed from the surroundings. A common example is photosynthesis. Knowing which type of reaction you're dealing with helps with lab safety and understanding energy flow in biological systems. Here's an example of an exothermic reaction. CH4 plus 2O2 produce CO2 and 2H2O. Delta HRXN equals negative 802.3 K. This means that 802.3 kilojoules of heat are released for every mole of methane combusted. The negative sign confirms that this reaction is exothermic. This is exactly why methane is used as fuel. It releases a large amount of heat when burned. Now let's look at an endothermic reaction. N2 plus O2 produce 2NO. Delta HRxn equals to positive 182.6 kilojoules. This means that 182.6 kilojoules of heat must be absorbed from the surroundings for every mole of nitrogen reacting with oxygen. The positive sign tells us energy is going into the system. These types of reactions require a constant energy input to proceed and are often slower or need a spark to start. Just like with masses or moles, delta HRxn follows stoichiometric rules. The amount of heat released or absorbed depends on how many moles of reactants are involved. For example, if the delta HRxn is given for the reaction of 1 mole of substance and we react 2 moles instead, the heat changes proportionally. That's why we always pair delta HRxn with a balanced equation. Here's a practical example involving propane, a common fuel. C3H8 plus 5O2 produce 3CO2 and 4H2O. Delta HRxn equals to negative 2044 kilojoule. So burning 1 mole of propane releases 2044 kilojoule of energy. This value acts just like a mole ratio. You can use it to convert from moles of propane to kilojoules of heat released and vice versa. This is especially useful in both chemistry and energy-related fields. Now let's say you're given a mass of propane and asked to find the total heat released. Here's the solution map. Convert grams of propane to moles using molar mass. Use the balanced equation to convert moles to kilojoules using delta HRxn. This step-by-step approach is the same method we've used for mass-to-mass stoichiometry, just with energy as the final product. In example 8.7, we're given 1.18 times 10 to the power of 4 grams of propane in a barbecue tank. The question is, how much heat is released if all of it is burned? Steps. Convert grams to moles using molar mass of C3H8, 44.11 gram mole. Use delta HRxn equals to minus 2044 kJ per mole of propane. This will give you the total kilojoules of energy released. Make sure to include the negative sign since it's exothermic. And always double-check your units. Let's look at another energy stoichiometry example. The reaction is 4NH3 plus 5O2 produce 4NO plus 6H2O. Delta HRxn equals to negative 906 kilojoule. Now the problem, what is the heat released when 155 G of NH3 reacts completely? Steps. Convert 155 G ammonia to moles using ammonia's molar mass 17.03 gram per mole. Use the balanced equation to determine heat using delta HRxn. This is a very common type of test and lab problem. Now let's level up with a challenge. Given the reaction, C4H10 plus O2 produce 4CO2 and 5H2O. Delta HRxn is negative 2658 kilojoules. Question, how many grams of butane are needed to produce 1.5 times 10 to the third kilojoules of heat? And also, how many grams of CO2 are produced? This two-part question tests your ability to go from energy to moles to mass of reactant and then from moles to mass of product. These are the exact calculations we do when designing fuel-efficient systems, or in pharmacy, calculating dosages based on energy demand. Let's connect all of this to something familiar, Bunsen burners. The flame you see in lab is caused by burning methane, CH4. The color and heat of the flame depend on how much oxygen is mixed with the methane. With little oxygen, the flame is yellow and sooty. This is incomplete combustion. With the right oxygen level, it becomes a clean blue flame. This is complete combustion, which is both hotter and more efficient. So even in basic lab tools, stoichiometry and combustion principles are in action. This image shows different stages of a Bunsen burner flame. On the left, not enough oxygen producing a yellow smoky flame. In the middle, optimal air intake, hot blue flame with a sharp inner cone. On the right, too much air can make the flame unstable or even extinguish it. Understanding this helps you work more safely and effectively in the lab. Let's review the big ideas from this chapter. A balanced chemical equation tells us the quantitative relationships between reactants and products. We use mole ratios to convert between substances. We can convert between grams and moles to perform real-world calculations. All of these skills are called reaction stoichiometry, and they help us make predictions and analyze reactions in the lab, clinic, or environment. Next, let's review the concepts of limiting reactant, theoretical yield, and percent yield. The limiting reactant is the substance that gets used up first. It determines the maximum amount of product that can form. The theoretical yield is how much product you could make based on the limiting reactant. The actual yield is what you actually get in the lab. And the percent yield helps us evaluate efficiency by comparing actual to theoretical yield. These concepts are not just academic, they apply directly in pharmaceutical manufacturing, food chemistry, and even diagnostics. Finally, we revisited the idea of enthalpy, or delta H, Rxn. This tells us how much heat is released or absorbed in a reaction under constant pressure. A negative delta H means heat is released, an exothermic process like combustion. A positive delta H means heat is absorbed, an endothermic process like photosynthesis. And remember, enthalpy is tied to the amount of material reacting. The more moles, the more heat exchanged. Let's recap your learning goals for this chapter. You should now be able to recognize stoichiometric relationships in a balanced equation, perform mole-to-mole conversions, perform mass-to-mass conversions using molar masses, identify limiting reactants and calculate theoretical and percent yields, calculate the heat emitted or absorbed using delta HRXN and stoichiometry. These are foundational skills that you'll use in many areas of health and clinical science. Let's finish with a real-world application. Every year, the world burns the fossil fuel equivalent of 9.0 times 10 to the 12 kilograms of petroleum. If we assume all that fuel is octane, we can calculate how much CO2 is released using this equation. 2 octane plus 25 O2 produce 16 CO2 and 18 H2O. This is a great example of using stoichiometry to understand large-scale environmental impact. This isn't just chemistry, it's sustainability. So how long would it take for fossil fuel combustion to double the atmospheric CO2 level? If the atmosphere currently holds 3.0 times 10 to the 15 kilograms of CO2 and we release around X kg a year, we can estimate how many years it would take to double that amount. This is a powerful demonstration of how chemistry connects to global climate challenges and how stoichiometric calculations can help us understand and solve them.